professor in computer science at Uppsala University. He works in the intersection of design and implementation programming languages, and most of what he does somehow ultimately comes down to memory management. Today's talk, the title of today's talk is How Should We Evaluate Garbage Collectors? So the floor is yours.
Thank you. All right, so let's do that. And let's do that. And let's do this. So let's see. Excellent. Right. Yes. How should we evaluate garbage collectors? So I originally had a somewhat more ambitious talk plan, but I couldn't really fit all of this into the 1 hour slot. So I scaled down my ambitions ever so slightly. Right. So this snake oil picture is not a dig at anyone or anything in particular. I tend to add a snake oil picture before any benchmarking result I present these days, mostly because, well, yeah, it's very easy, as we all know, I think, in this room, to get things wrong, even though you didn't intend to get it wrong, right? So to the extent you should believe benchmark results, well, you know, the devil is in the details, right? So, yes, this talk is, starting out well. I'll try and put that back. Right, so the gist of this talk is about convincing you people in this room and people listening that, I mean, when we evaluate garbage collectors, we want to really explore the entire deployment space, right? We want to see both memory use of high and low and go all the way up to sort of all of the memory that the systems are using, and we want to look at the CPU dimension in full as well. So that's sort of the thing that we want to look at. And my claim in this talk is essentially that what we are doing currently is we are looking only at one corner of this space. So we're constraining our evaluations to one particular corner of the space that we should be looking at. And the problem with this is that what we find when we look at that corner looks very little like what we find in the other part of the spectrum, right? So we're studying this gnome corner, right? And this gnome looks very little like the beast that we might find on the other end, right? So that's sort of the point I'm going to try to make to you. Okay. Great. So yeah, I'm going to be focusing on Java GC because that's essentially the thing that I know. And so let's start by looking at how do we evaluate Java GC today, right? And this is based on a survey of the last couple of years of GC papers in this space, so 34 papers in total. Okay, so how do we evaluate Java GC today? Well, as should come as a surprise to no one, probably. The Java evaluation space is dominated by the da capo benchmarks, right? So out of the 34 papers we looked at, 28 used da capo to evaluate GC performance, right? So da capo is dominating this space, and that's a good success and a testament to the quality and the ease of use of the da capo benchmarks that Steve and people around him have been developing, right? And the community is sort of quick to adapt to the new releases, at least the last release, the 23 release, is now dominating. I mean, it's actually dominating almost before it was officially released because you could already pull it off of GitHub and use it, right? And so we were seeing some uses of the original 2006 release going up to about 2021. And then that tapered off. We were seeing from the 2009 release, but now really the latest release is dominating. So people are following the development of this benchmark suite and are running the latest and greatest. So that's great. Okay, good, right? So the da capo benchmark suite comes with a couple of workload sizes, right? So there are the small workload sizes, the default ones, and the large ones. And well, there are some like very large ones for some specific benchmarks. There used to be a huge workload size that's, I think, now discontinued for the latest release. But what do people use? Well, people predominantly use the default workload sizes, right? So, like, that's the one that's dominating this space, right? So sometimes we see, for example, someone use small because they want to run stuff in a simulator, and that's good for possibly good for making the simulator run faster. Right. So in the Java space, when you want to understand the performance of garbage collection, then the concept of a heap size is super important, right? Because when you start your Java process, you need to tell it how much RAM can we use for on-heap memory, right? And that controls things like the frequency of garbage collection, right? So back in the day when we had mostly throughput collectors, you might give the Java process some kind of maximum heap size, and it would sort of use all of that heap space until it hit the limit, and then it would stop the world, do some GC, and then continue going again. And today we have more concurrent collectors, so we're using slightly more complicated heuristics where the goal may be to sort of keep the GC performance on par with the allocation pressure from or the allocation rate of the program, right? So obviously, when we evaluate GC, picking a good heap size is super important, right? Because that will really control the GC performance of the benchmark, right? So what do people do? Right, so the predominant method for picking a heap size is this thing called the minimum heap method. Right, so it is essentially finding the smallest possible heap that you can use to run the program reliably without crashing, and then use that as your starting point for an exploration. So you might start at the absolute minimum heap and see, okay, when we're really starving the system, how does it perform? And then we give it maybe 2x that heap or 3x that heap, and so on and so forth. That's the predominant method. There are a bunch of other methods. Fixed heap size is typically, I mean, it's just finding a heap size and sticking to that. Could be because we've determined that the benchmark has its peak performance, or displays some interesting characteristics at that point. The concept of a stall-free heap, now we're going away from the minimum heap size, right? So to a more, let's say, concurrency-oriented way of thinking, right? So with a stall-free heap, let's pick, it's basically the minimum heap size, but changed for a concurrent world, right? So what's the smallest possible heap with which we can reliably run this program without the GC getting on the critical path of performance, right? What's the smallest possible heap that allows the GC to keep up with the pace of the allocation of the program, right? Right. So yes, so minimum heap sizing, that's dominating the space. And what are the minimum heaps that people use to explore? Well, they look a bit like this, right? So the absolute dominating maximum heap size factor is 6x, right? So that means if you have a program with a minimum heap of 100 megabytes, you will explore that up to 600 megabytes of RAM. That's what you're going to give to the JVM when it starts up, right? So in summary, like, the capo is dominating this space. It's the latest release that are dominating the latest papers. Most people use the default workload size, and they use the minimum heap method for measuring or for deciding what's a good heap, and they scale this up to a maximum factor of 6x. All right, so that's the software side. Now let's look at the hardware side. So what are the machines that researchers use in these 34 publications to evaluate GC, right? So they're using fairly modern hardware. You can't see a time axis now on this, but as you would expect, it's sort of becoming more and more resourceful as time goes on, right? So we're seeing sort of 16, 32, 64 core machines. And in terms of memory, if you remove phones and sort of very particular deployments, you have sort of a minimum of 1 gigabyte of memory per core. But as you can see, frequently it goes above that that ratio, right? So smartphones have smaller amounts of memory, so we're seeing, let's say, half a gigabyte per core, or 0.75, something like that. So those are the machines that we are using to run these benchmarks, right? And if we look at cloud machines, so looking at AWS, Azure, GCP, OCI, we see cloud instances that you can sort of buy off the shelf with these configurations, right? So you have a bunch of different configurations of different sizes. They correspond fairly well to the machines that researchers are using, and sort of the general purpose here is at 1 gigabyte per core, roughly, and then you can go above that. The absolute smallest one you can get some container-based configurations which are available with up to 4 cores, right? And then you can get below the 1 gigabyte per core line, typically. All right, so now we know the machines that we're using. So let's look at the scalability of the capo's default workload sizes in terms of CPU. Right? So this is an experiment. Now we gave these benchmarks 48x the minimum heap that they required, and we ran them on a 36-core machine and sort of looked at how do they scale, and this is the result. So most of these benchmarks do not scale, and that's precisely what they're intended to do if you follow the documentation. Then some of the scaling benchmarks, they seem to taper off at 4, 5, 6 cores, and if you go all the way up to 36 cores, then it's Sunflow and Zebra Crossing, or however you would pronounce that, that sort of allows you to explore all the way up to the limits of the machine. So it's 34 cores is where these peak out in this experiment, right? So that's CPU scaling. Let's look at memory now. All right, so the Da Capo default workload size has a geometric mean of 63 megabytes, right? So this is not per core, now this is the entire program, right? So it sort of has this distribution from Aurora, which uses 5 megabytes of heap, all the way up to H2 that uses 681 megabytes of minimum heap, right? And of course, what the minimum heap is will vary a little bit with what is the deployment configuration you're using, but these are the numbers that Da Capo itself reports, and I'm sure Steve will correct me if I'm wrong. Right. So if we map this back to the machines, right? Then if we take this minimum heap size method and we start with the minimum heap sizes that we get from the benchmarks, and we try and explore it up to 6x, right? And we sort of map this back to the machines that we have and see how much of the machines we are using. Well, then the picture looks a little bit like this, right? So 75% of all of the configurations that we are testing, they use less than 1% of the available memory on the machine. So we're not using a lot of the available memory, as you can see, right? And if we change this to run the sort of the small container-based systems instead, with that typically has fewer amounts of cores, then well, we get to 75% of the configurations use less than 20% of the machine. So what does that mean? Well, I mean, you can interpret this in different ways, but our interpretation is that there's really a mismatch here between reality and how we evaluate GC, right? So if we, again, look at every red dot here on this graph is one actual configuration used in these 34 papers, right? And so that means that someone was using an 8-core machine with some amount of memory, for example, right? And so we have a thick line at 1 gigabyte per core here, and we're sort of plotting how much of the memory that's available that we actually use, right? So you can see most of these configurations fall well below this 1 gigabyte of memory per core ratio. And if we look at where the machines are, well, they're all up here, right? So they are above this line. So this is what I mean when I say there is a mismatch, right? We're evaluating things at sort of a space that's not really representative of the machines that we have on hands, right? So in summary, we're constraining our GC evaluation to just a small corner of the deployment space. And more speculatively, perhaps, you could make the argument that most GC evaluations use configurations which are unlikely to be used in real deployments, right? Because if you have a 64-core machine, you probably have 64 gigabytes of RAM or more, and we are constraining the programs to run at a small fraction of this available memory, right? If we gave it a little bit more, then maybe some of these effects of memory would taper off, right? So why are we doing this? Do we really think that the results that we are getting in this gnome corner there is sort of representative for what we get in the more beastly direction, right? So let's explore this a little further. So we're now going to be looking at a bunch of heat maps, right? And so these heat maps is an exploration of the da capo default workloads, right? So on the x-axis, you have the number of worker threads that we give to the program. So 1, 2, 4, 8, and 16. And on the y-axis, you have the amount of memory that we give to the programs. In this green rectangle, you see this is the space that would be explored if you use the minimum heap size method and you scaled up to 6x. Right? The black rectangles, that's the 1 gigabyte per core configuration. Right? If it's white space down there, you can see that's out of memory, right? So we're seeing, let's see if I can get a cursor in here. No, apparently not. But yes, you can see the space there, right? So this particular benchmark could not be run with a 37 megabyte heap or smaller, right? Yes, so what are we seeing in these cells? So in this, we're currently looking at throughput. We're going to be looking at more of this for more benchmarks. I'm just trying to tell you the notation right now, right? So 1.0, that's the highest possible throughput, right? So everything else is a factor slowdown, right? So 3.0 means this is a 3.0x slowdown of the maximum throughput that we could get. Right, so we're now going to look at 10 of the da capo benchmarks, the ones that report that they are trying to scale to to use the resources available on the machine, right? So throughput numbers, right? So what do we see? Well, we see first thing that you can notice that there is very little overlap between this green rectangle and this 1 gigabyte per core rectangle, right? So the black outlines and the green outlines, they rarely overlap, right? So H2, for example, is a good exception, right? So there they almost completely overlap, right? Because H2 has this 681 megabyte minimum heap size. If you go down to smaller worker thread counts, right? So we're sort of running the benchmark on a smaller number of cores, if you will, then we might see some overlap, but mostly the green space and the black space isn't really overlapping at all. And if you look at the bottom rows, right, you may see that giving the benchmark a little bit more memory seems to have some effect, but as soon as you go sort of a little bit higher up, then it's all down to how much CPU we throw on this, right? And so currently the da capo workloads, in the programs we're looking at now, they're defaulting to use as many worker threads as you have cores on your machine. So you would be looking at the 16 column, right? Okay, so right. So this is some way of looking at like if we were to run these programs with the amount of heap that's available on the machine, what's the effect of that? What would we see? So the effect is not so pronounced when it comes to the throughput results. Let's see if it's different for CPU utilization. Right. So now exactly the same kind of heat maps again, but now in each cell, we're looking at the amount of cores that were used on average throughout the entire execution. So 10.9, we're using almost 11 cores at full speed on average throughout the entire execution of this program, and 1.6 means we're using 1.6 cores on average throughout all of this, right? And the green stuff and the black stuff, it's all the same. The only thing that's changed now is what's the meaning of the numbers in the cells, right? And so now higher is more CPU, right? All right, so what does that look like? Okay, so it looks a bit like this, right? So yeah, the overlapping of the green and the black, that's of course going to be the same, right? That nothing has changed here. We can see that in terms of what programs really scale up to use most of the machines. So we have Sunflow and we have Zebra Crossing, right? That's the ones where you can, if you wanted to test if your GC and your mutator thread is fighting over CPU resources. Well, those two benchmarks might be able to give you a good feeling for that. But most of the others on a 16-core machine would give ample resources over to the garbage collector to do some work, right? So you would not be testing that particular scenario, right? And of course, we might want to test both these cases at the same time, right? In different benchmarks. Right, so CPU utilization, right? And yes, so most programs give you ample CPU headroom, right? And then finally, let's look at GC cycles per second, right? So now the numbers represent how many times did we do a GC cycle per second when this program was running, right? And so the black rectangles, they still stick, but now we're coloring them red in the case where we're seeing less than one GC cycle happening per iteration of the benchmark. So, right, so yes, and so for example, in this particular case, we see 230 GC cycles per second at the very bottom right corner there of the green rectangle, but just the one GC cycle per second for all of the red rectangles, for example. Right, so this is what we see, right? So notably the bottom rows here see very high frequency GC, right? So we're seeing sometimes, especially if we're looking at the 16 worker thread configurations, right? Where there are 16 threads that can now allocate data, right? That's of course going to exhaust the amount of memory that we have given to these programs faster, and so that will increase the GC frequency, right? So we're seeing numbers in the hundreds for the very smallest possible configurations at the highest possible number of worker threads, right? And so this would not be possible if the benchmarks were using more memory, right? If they had a larger live set, that we would see a different cost profile, and you can see that if you look at H2, for example, there, even at the smallest possible configuration or memory configuration with the highest number of workers, you see 28 GC cycles per second. So that's like an order of magnitude less than many of the others, right? And that's because there is a lot of work for the GC to do in a cycle, because it has a larger live set, right? There's more memory to traverse, to mark, whatever is the algorithm, right? Oh, I should say, I forgot to point that out. These are all numbers now obtained with the G1 default garbage collector of OpenJDK 25, right? So this might look different, of course, if you run it with a different GC, but this is the default GC that I'm going to use as a baseline for essentially everything I'm telling you today. Right, so if you give these programs the 1 gigabyte per core that you have most likely, right, on most of these hardware configurations that we have seen, we're seeing fewer than one GC cycle per benchmark iteration. So that means if you're running 20 iterations of a benchmark, and maybe you're discarding the first 15 ones, and then you're looking at the average of the last 5 ones to get some kind of steady state, some of these iterations might not see any GC activity at all at this deployment, right? And so, I mean, in order to see GC activity, you need to, with these benchmarks, right, you need to press basically the amount of memory down in order to trigger more GC activity. But since we have pretty small live sets, there is not much memory used in these programs. I mean, we can see these very high numbers of GC cycles per second. That wouldn't really be possible if we had larger live sets, right? So, summarizing that, right? So again, we do not really explore this deployment space well, at least if we look at sort of what do people predominantly do with the best tools that we have at hand, right? We see this mismatch between CPU and memory, right? We're sort of running at the most CPU that we can use. So we're essentially treating CPU as a sort of free resource, but then we're constraining the memory that we're giving to these programs to a very small amount in order to sort of get some artificial GC pressure, if you will, out of these benchmarks, right? And the benchmarks live sets are very small, so that means you can have these sort of high sustained GC frequency, right? And we also see that there's ample CPU headroom in many of these, right? Yes, and as I already pointed out, right, if we size the heaps sort of according to what is the memory that exists on the machine, we'll see very frequently less than 1 GC cycle per iteration, right? Okay, great. So now we looked at the da capo default workloads, but da capo also has a large workload in the 2311 release, right? So let's do a little experiment, right? So let's start in the corner of the gnome and then sort of move a little bit towards the beast and see, like, do the results that we get when we are looking at the gnome hold up if we're running with the larger workloads, right? So do the results hold up if we increase the workloads, right? Okay, so a little bit of background, right? So I said we have the small, default, and large configurations for the benchmarks, right? So small, 5 to 157 megabytes of heap, and then default from 5 to 681, as we have seen before. And now we're going up to large, right? So large is 13 megabytes to 10 gigabytes, right? So 10 gigabytes, that's a substantial increase of a workload, but that's not all of them. So the geometric mean is 215 megabytes now, so at least we're seeing the next order of magnitude, if you will, right? So in this study, we're going to be focusing on those benchmarks that have a minimum heap size of at least 1 gigabyte, right? So we're going with Batik and BioJava, GraphKey, H2, H2O, and PMD. And then we took the Salon benchmark, which is just processing XML files, and we replaced some of the small XML files with larger files. So then we could grow the minimum heap size of Xalan to 1.8 gigabytes instead of 13 megabytes, which was the large workload standard, right? Okay, so we're now going to look at these 7 benchmarks and comparing the results obtained in default with the results obtained in large, right? But before we do that, let's look a little bit at what's the effect of the GC cost of, the CPU cost of a GC cycle in relation with the large and default workloads, right? So now we're looking at the heat map where we have the benchmarks on the y-axis and different heap factors on the y-axis, and we are in each cell figuring out what's the cost in GC CPU for the large workload per cycle, and dividing that by the cost of a cycle in default benchmarks, right? And so what we're seeing is a pretty big change, right? So there's somewhere between 2.2 and 121 times the higher cost in large, right? And of course, the freak result here is really the Salon benchmarks that we cooked up ourselves, not in order to get to this result, but just to increase the live set a little bit. And this is the result we got. But if you remove Salon, then you're seeing somewhere between 2 and 25x cost per GC cycle, right? So the cost profile is different, and it's also like a non-linear relationship really between the costs in default and the costs in large, because sometimes we see for H2, for example, like the more heap we give to the benchmark, the cheaper each GC cycle is, but that's not the case in H2O, for example. If we give it more heap, then each GC cycle is on average more costly, right? So we're seeing some interesting effects, right? So before we look at default versus large, let me just quickly plug some work done by Jonas, my PhD student. So in order to get this GC CPU measurements, he contributed to OpenJDK. That's now in production since OpenJDK 26. So if you give OpenJDK this xlog:CPU flag when you run it, then when the VM tears down, it's going to print this table that breaks down the costs of the various VM threads, right? So you will see exactly what was the cost of GC threads, and also in the serial collector where you're just reusing the main thread, that's going to be correctly accounted as well. So you can get a very nice breakdown of the GC CPU costs with some telemetry that is now in OpenJDK ISMM'26. Jonas has a nice blog post about this if you want to go look at it. I should point out the caveat that the barrier cost in mutators is not included, and this is, I mean, that's the big challenge, right, that we will eventually have to tackle, and this is super hard to do in an automated way, and it's super hard to do without getting all of these Heisenberg effects when you are trying to measure these things. But this is a step in the right direction, we think, and you can also, from within your Java program itself, query the results of like what's the GC CPU cost right now using this memory MXB. So you could use that, for example, to build an adaptive GC that looked at like what's the cost profile, what is the amount of CPU I'm willing to spend on GC, and adjust that using that number, for example. All right, good. So now let's look at some result comparisons, right? So let's start with JDK 11. So we're now going to compare this super cool LXR collector that was built in Steve's group with G1, right? Going from default to large, right? And so what we're looking at in each cell here is now basically the throughput. So you can think of that as the time it took to perform an iteration divided by the time it took to perform an iteration in G1. So G1 is always going to be at the bottom of all of these figures I'm going to show you, right? So that means that if we have a number that's smaller than 1, then LXR was faster. And if the number is larger than 1, then LXR was slower than G1. So let's look at Batik, for example, right? So in Batik, LXR was slightly slower than G1 in the default workloads, right? So 4% slower, 2% slower, and then, I mean, it's essentially on par, right? And then those effects are slightly increased when we go over to the large workload, right? So LXR was trailing a little bit, and then it's trailing a little bit more in the large workloads, right? If we instead look at BioJava, then LXR was 12% slower in the tightest possible heap, right? But then when we moved to large, all of that was essentially eradicated. It's almost on par, right, in the large workload. And interestingly, in the 2x and 6x and 12x heap factors, like LXR was faster than G1 on all of these configurations. But again, in large with the same heap factors, we are seeing almost an on-par result, right? So something is happening, both going from a regression being turned into on-par, and from an increase being turned into on-par, right? Let's look at H2O. Here is a super impressive result for the LXR collector, right? It's more than 30% faster. This is super cool, right? On the 1.3x heap factor. But again, going from default to large, right? We're seeing a 30% improvement turn into a 20% regression. So there is a huge difference there, right? And similar, very nice result on 2x, turn into a regression in large, and then on the 6x and 12x, then apparently G1 sort of seems to perform better if we give it more headroom, or alternatively, G1 requires more headroom than LXR, if you will. Then like regression is turned into an even bigger regression at the 6x and 12x heap sizes, right? Okay, so we can try and aggregate this in some way. So let's take the geometric mean of the default and large throughput numbers, right? So we see that on average, right, for the 1.3x heap size, LXR is a lot faster than G1. Right? Super nice result in the default benchmarks. But when we go to large, then that's turned into a regression, right? Same thing with the 2x heap size. It's an improvement that's turned into regression. Then it's an on-par result that's being turned into a regression, and then a regression that's being a little bit increased by going to the large workload size. So we're seeing like a 9% improvement going to an 8% regression by switching from default to large workloads, right? Okay, so let's move ahead to OpenJDK 25. So now let's look at ZGC versus G1 on OpenJDK 25. So default versus large again, right? So maybe the first thing to note is that a lot of these really tight heap factors we cannot give you a result for. That's because ZGC just the algorithm fundamentally needs more memory, so it ooms on many of these very tight heaps. But if you give it slightly more memory, it will run, right? So 3x, 6x, and 12x, we mostly have results for all of these configurations. So now, less than 1 means that GC was faster, and greater than 1 means G1 was faster. So in Batik, right, we have 0.05 result for ZGC, so 5% slower, and 6% slower when we go to large, 2% slower on 6x in default, going to 1% slower on large, and then slight regression on 12x is turned to essentially an on-par result in large. Right, so there are changes here as well. Looking at H2O, right, there is a huge regression for ZGC on the 3x heap size, so it's 70% slower, right? But when we go to large, almost all of that is removed, right? So it turns into a 4% regression instead. And sort of similar for 6x, now given more memory, it still was running slower than G1, but in default versus large, we see a lot of that being changed or reversed, right? And on par, given enough memory in both default and large, right? So summarizing all of that, right? So we see we're going from regression to, again, regression, but a much substantially smaller regression, right? So we're going from a 32% regression to a 7% regression in total by going from default to large workloads. Right, moving on, let's look at the last comparison. Now this is parallel GC versus G1, again on OpenJDK 25. Right? So in this case, less than 1 means that parallel is faster, right? And so, right, let me back that up. Right, so rather than going through and looking at all of the individual benchmarks, you can see if you look at them, like some go in one direction, others go in another direction, but on average, if you permit us to aggregate them using the geometric mean like that, well, it seems that there is really no difference when going from default to large on the 3x and 6x heap sizes. However, on the 12x, right, so we saw parallel was slightly faster on 12x, but then it's a lot faster on 12x with the large workloads. However, on the very tight heap, right, so we have a huge regression on parallel for these benchmarks, turned into still a very large regression on large, but substantially smaller, right, from 2.59 to 1.7, right? So all in all, it's 25% regression turning into a 12% regression, right? And you could ask, like, is this a valid way of counting? Well, it depends, right? I mean, I think implicitly in this way of looking at it, we are saying every configuration has equal weight, right? The 1.3x heap and the 12x heap, they are worth the same, right? You could argue something differently, but in this case, we're saying they are all equally valid configurations. Right, so in summary, we're seeing pretty large changes when we go from default to large, right? So it's a 20% difference in LXR, there's a 25% difference in ZGC, a 12% difference for parallel, right? We're seeing improvements turned into regressions and regressions turned into smaller regressions, and we're seeing some results holding up in parallel, but then when heaps are tight, there are very big changes in the results, right? And this is like more than what most papers demonstrate when we sort of make improvements to our GC algorithms, right? And this is, of course, because the cost profile for these larger live sets is fundamentally different, right? So we're not like flushing our T-labs a couple of 100 times per second, and we might not be scanning RAM sets or whatever it is we're doing, depending on the algorithm, right? So there are other factors now that start to dominate the cost profile of doing GC, right? And this is not just OpenJDK 25, right? This is also on OpenJDK 11. It's not just production GCs, because we also use the mature LXR version, right? So like this seems to hold up, right? So you might ask yourself, is this just a consequence of the capo then? Right? So let's try and answer that question briefly. Right? So now let's see if we can reproduce these results using SpecJBB 2015. Right, so SpecJBB 2015, this is a program that's simulating a web store, essentially. Right? So you have customers coming and buying goods from this web store. And what we are going to do now is we're going to take some constants in the SpecJBB 2015 benchmark, which is the number of items that in the store, customers, and the retained receipts. And we're going to scale that up and down because that will vary the live set of the program. Right? The algorithm is still the same, the sort of the number of requests that are being made, the relation between saturation requests and probe requests is exactly the same, but the live set is different. Right? And we use that to create a number of different workloads. And let's see if what we see in these results looks similar to what we just saw in Da Capo. Right? So, okay, so we have these 8 different workloads, A to H. Should point out F is sort of now the workload factor, the one we use to scale all of the number of items, customers, and retained receipts is 1. So this is essentially your vanilla SpecJBB 2015 configuration, right? So that's F. So we're scaling things down a little bit, going to the left, and we're scaling things up, going to the right. So we can look, for example, at the A and B configurations here. So now we're giving these programs 0.5 gigabytes of heap. So these are running now very constrained, right? Sort of similar to kind of a min heap situation, if you like, on a 28-core machine. And sort of the min heaps that we calculated here is 0.4 and 0.45 gigabytes. So we're running fairly close to that space, right? And now the workload factor for the A and B configurations is scaled down by 10 and then another 10 times to get from B to A. Right? And that has some impact on the live set, as you can see. Right? So what do we see? Well, when we go from A to B, right? So we're essentially touching the live set a little bit. It's a 33% increase of the live set. Right? So we see throughput reduction for A1. That's the blue bar up there, of 20%. Right? If we look at the D and E configurations, which are similar to F, right? We're giving it again 28 gigabytes of memory, right? So that's 1 gigabyte per core. And we in the E workload, we've scaled down the number of items, customers, and retained receipts by 10, factor 10, and then we're doing it again to get from E to D, right? So we're seeing some substantial changes in live set here, right? So we're going from 0.27 live set in the D configuration and 0.4 gigabyte of live set in the E configuration to 2 gigabytes in F, right? So it's sort of, again, similar to going from default to large, if you will, in Da Capo. And we're seeing some similar results here, right? So we're seeing a reduction in throughput from D to F of about 18% and from E to F, 22%. And if we bring latency into this picture, then the effects are even more pronounced, right? So going from A to B, that's a 50% reduction in latency operations per second, 40% for D to F, and 46% from E to F, right? So we're seeing sort of similar kinds of effects here, right? I should point out this H configuration is pretty unusual, right? So it's 768 gigabytes of memory for a 28-core machine. I mean, that's something that you can find in one of these cloud configurations, for example, if you will, right? And if you're running that, you can see some interesting results that, for example, the latency score of ZGC is really showing off there its algorithm. Right, okay, so let's look at GC cycles per second. All right, so again, in the very constrained heaps, we're seeing, just as we'd expect, a higher GC frequency, right? So it's not up in the hundreds yet. It's almost going there in the B configuration for the 0.5 gigabytes of RAM with the 0.45 minimum heap size, sort of 60, 70, somewhere there in that space. For the ones where we have about 1 gigabyte per core, we're seeing numbers of roughly around 1 GC cycle per second, right? For those configurations, right? And if we look at GC CPU, well, so it's pretty clear that when you scale up these factors that increase the live set, you're seeing sort of an additional cost in terms of what the GC needs to do, even at this small number of cycles per second, right? Compared to what we've seen for those other benchmarks, right? So the cost profile again is different, right? All right, yes. So let's summarize, right? So SPECjbb 2015, right? Experimenting with this benchmark seems to say that, well, this is certainly not an effect of the capo, right? This is something that is perhaps more fundamental to GC, right? So varying the live set will change the results significantly, right? Using more memory will change the results that we report in evaluations, right? And it also suggests that these small workloads, right, they shouldn't be used as proxies for what we'd see in the larger workloads at all, right? So I mean, sort of what we are doing isn't necessarily representative of what our users, the ones we are building these GCs for in the end, right, are likely to see, right? Okay, so let's get a little bit constructive, right? So where do we go from here? Well, so I think a first thing we should do is we should not use the minimum heap size methodology. We should instead use something that I would like to call representative heap. So we start with deployment-based heap sizing instead of workload-based heap sizing. So we're looking at what are the systems for which we are building these GCs out there, and then we start from there, right? So for a general purpose system where we're expecting to have about 1 gigabyte per core, well, that's a good starting point for what is the amount of memory that we should give to the programs, right? And then we can sweep up and down in fixed increments instead. So maybe 250 megabytes per core or whatever is reasonable, right? So that gives us sort of deployment sensitivity over workload sensitivity. And that's nice because sometimes when you see like, okay, so we're running this now with a 6x min heap, what does that mean? Well, it means very, very different thing if your min heap is 13 megabytes or it's a 681 megabytes, right? If you have a GC that's using 2 megabyte per core T-labs on a 32 core machine, well, you're eating up 64 megabytes of RAM to those T-labs immediately, right? And so giving a program 78 megabytes of heap may seem like it's an ample overhead, but it really isn't. And I guess this is like because we're building GCs today for like a different class of machines than what we used to do some time ago. So if we now take these representative heaps and we start using them, what's the consequence? Well, the consequence is, of course, we need to use the benchmarks that I mean, I would argue that we need to do that anyway, but we need to change the benchmarks to fit the machines that we use to evaluate GC, right? So we want them to be more scalable in terms of CPU, and we also want to have these larger live sets. We need to use more of the memory that's actually on the machine, right? And with sort of working with what we have today, I think we need to change the way we run these existing benchmarks. So for example, if we aren't using more than a couple of cores of the machine, well, why don't we constrain the evaluation to just run on that machine? I mean, who would run something that scales to 6 cores on a 64 core machine? I think that is an unlikely deployment. It would be more interesting to run it, limiting it to 6 cores, right? And that might also push it down into the representative heap sizing, right? Because if we're running with just 6 cores or 0.5 vCPUs or something like that, then of course we should also give this program less memory as an effect of that, right? So that, to some extent, removes problems with varying the free resources that we give to GC, because we're removing some of the free CPU. And I would also say that we should favor running these large workloads that are already there, right? That Steve's group has already engineered for us instead of the default ones, or maybe run both to show what is the sensitivity to workload sizing, right? Because still the large workloads, they are not that large in relation to the machines that we are using. But I mean, in lieu of having benchmarks that capture all of that space, then at least if we can see something along the lines of what you'd expect to see when benchmarks scale up in terms of live sets, that would be interesting, right? And of course, we have no way of knowing that if we scale up to the full extent of the machine, then maybe these results that we saw going from default to large might flip again, right? We simply do not know, right? There's nothing that says that this needs to be sort of a monotonic change, right? And as a consequence of this, it also means that GC benchmarking will take a little bit more time, but I think this is a good time investment, because I think that means that the results that we are producing are more meaningful for the systems where these GCs are likely to be deployed, right? And a lot of this work can be done with just what we have today, right? So you could, for example, change some of the existing Da Capo benchmarks to have a larger workload. So this is an experiment changing Cassandra from 150 megabyte live sort of minimum heap to 1.5 gigabyte minimum heap, right? And 1.5 gigabyte is still pretty small for a Cassandra deployment, but it is different than, I mean, considerably larger than the 150 megabyte. And again, we can see latency effects immediately as a consequence of that. And they, as I said, they might flip again when we go up to, let's say, a 15 gigabyte minimum heaps. We simply do not know, right? And we do not present these evaluations in our papers, right? So here is an example of what such a sweep could look like, right? So now we're looking at SpecJBB, and we're varying the amount of cores that we give to SpecJBB and the amount of memory that we give to SpecJBB. And that means that, like, if we're looking at just a row with a 4 gigabyte heap, but going all the way up to 64 cores, well, that's 64 megabytes of memory per core, right? So that's a very constrained configuration, whereas if you go with a 256 megabytes of heap on a 4 core, well, that's 64 gigabytes per core, right? So a lot. And by just looking at sort of the gradients of these, we can get a good intuition, or at least I feel we can get a good intuition for how these algorithms behave, right? So it's pretty clear that parallel, which is the top left one, right, in terms of throughput, as soon as you give it enough memory, that's somewhere between 16 and 32 gigabytes, I think some of the gradient effects aren't coming through perfectly on the beamer. But after that, it sort of doesn't really matter how much memory you give it. It's just CPU. That's the thing that matters. If you look at ZGC, well, you really need to give it a lot more memory in order to get to the same kinds of throughput results that that parallel will give you already at 32, right? If you look at latency, right now, sort of we're seeing a completely different way that the gradients are scaling, right? So sort of if we looked at throughput in parallel, it was horizontal essentially, and now it's almost vertical, right? So now the more memory we give it, that memory seems to be very important for getting a good latency result for parallel, and that's even more emphasized if we look at the strictest SLA, which is 10 milliseconds for SpecJBB, right? And it's pretty clear sort of where the ZGC algorithm tries to favor, right? And you can see the G1, which is sort of trying to deliver the sort of a little bit of both, right? It's trying to get good throughput and not too bad latency. It seems to be working out pretty well according to just this one SpecJBB result. So in conclusion, I think that data shows that we are constraining GC evaluation to just like a small corner of the space that we, I think, should be exploring, right? And many of the GC effects that we have, they vanish if we use representative heap sizing. So we scale programs up to the memory that we essentially already paid for in most of these cases, right? And I think we should adopt new workload sizes and benchmarks that permit exploring this entire deployment space. And I think, I mean, a really good way of doing that, right, is by leveraging this super nice deployment platform that exists thanks to Steve and the da capo benchmarks, right? But on the other hand, the large workloads have been around for a very long time, and it seems that they aren't being widely used and they're not widely reported in papers, right? So it's not just about changing the workloads, it's also about changing the mindset of our community to use these large workloads. And this is, I had on the previous slide, this means GC evaluation will take more time, right? Doing GC evaluation on the large workloads, that will run a lot slower than doing it on the default workloads. And that's probably sort of the effect that we are seeing. And maybe that means that we should just replace the meaning of small and large and default to something that sort of increases these numbers a little bit, gives you a slightly larger heap size. Right, oops. Final bullet on the final slide, so you don't need to stress tomorrow. Right, yes. And I think we should also switch from workload-based to deployment-based heap sizing, as I have said. Right, and that if we do that, that immediately stresses the limitations of the benchmarks that we have, because we're not running with these artificially small heaps. So that's it. Thank you.
Thank you for the nice talk. The time is limited, but I'd like to accept a couple of questions.
Thanks. I guess you're expecting a question from me.
I was, yes.
Yeah.
Or possibly a comment.
Yeah. So first of all, I think there's a little bit of a conflation of concerns here between benchmarks and methodology, and we need to be very careful to pull them apart. So when I was an undergraduate, back in a long time ago, I read Hennessy and Patterson, and the opening parts of that book talk about benchmarks and their role in computer architecture, but more broadly. And the point they make is that benchmarks can only ever be indicative. And if you have, and they tell an anecdote of a story of someone wanting to, maybe buy a database from either one vendor or another. And their point was the benchmarks might give you an idea about which of those databases is going to be better, but you as the customer, ultimately the only way you will know is if you deploy that database on your system with your constraints, with your workload. And so as a consumer, that's ultimately the only thing you can do. And benchmarks up until that point are only ever going to be indicative. Yep. So that I just want to make that really clear. I think we all know that, but I think it's worth saying that again. So there's a distinction between what you need in deployment and what a benchmark will do and what purpose a benchmark serves. Now, as far as Java goes, Java's been pretty well served by benchmarks compared to many of the other languages in the programming languages community. And as you know, we welcome contributions. So if you would like to contribute any of those things, the da capo project would be super happy.
Great. And I think the community, I mean, let's make sure that everyone in the community hears that that's not just an invitation to me, right? This is an invitation to anyone to work on this.
Absolutely. Yeah. And it's on GitHub, and pull requests are very, very welcome. So if we can improve those. So 100%, and I should have started by saying thank you very much for raising this, because I think this sort of discussion is certainly absolutely useful, both with respect to benchmarks, but also with respect to methodology. And I also want to point to one news paper from Uppsala last year, one news is sitting right there, which talks about almost exactly this question, and how to deploy, how to build a GC for an industrial, a hyperscaled service at Google. And how a benchmark suite like da capo, which has got holes, it's a very widely varied benchmark, how that can service that, and how to address almost exactly the problems you're talking about. So that was published at Uppsala last year, and if anyone wants to talk to Wenyu about that, he's sitting right over there. So I think that's worth noting. But the other thing I want to point to here is that the GC community is broad, and Java is a very important part of it, but it's only one part. I personally work on 5 different production runtimes. But I spend my working life working on 5 completely different production runtimes: Android, Chrome, the Ruby GC, the Julia GC, and OpenJDK. 5 different systems, and they're wildly different. And this touches on one part of the GC environment, but more particularly, it touches on the part that considers large-scale deployments. Now, large-scale deployments both cover compressed pointers, which is actually the majority. So 80% of large-scale services are actually running with compressed pointers. That means they're running in less than 32 gigabytes of total heap size. And those that use uncompressed pointers are probably only 20% of the large-scale service deployments for Java. So if we think about situations where the actual physical, where the heap sizes are bigger than 32 gigabytes, that's a very important space, but it is only a small part of the space of GC environments. So I just want to make sure we're totally on top of that. The other point is, and I guess perhaps the most important part, and the thing that worries me most about everything we heard, was the question of the economics of ignoring the baseline. Okay, so what the min heap is doing is saying, look, if pressed, we could run this particular workload, whichever workload it is, in this available space. And when we deploy it in a particular situation, it's very, very important to know that we're gaining a certain performance at this amount of cost relative to the baseline. And if we discard the minimum heap baseline, then we're not looking at the efficiency of that particular GC with respect to memory. And I think we can't dismiss that. So what because all of us as scientists are concerned with efficiency, and efficiency means measuring against some baseline. And so if this thing here can run in 2 gigabytes and we're using 64, we've got a 32-fold overhead.
So can I get a word in sideways?
Yeah.
Thank you.
I'm nearly done, by the way.
I mean, I agree with that, but I also think that when we are running with the smallest possible heap, we're only looking at memory, and we should be looking at both memory and CPU.
Absolutely.
Right? And I think that when you're looking at you can sometimes get an on-par result with 2 collectors, but then one is using 2 or 3 times as much CPU, or suddenly the benchmark with 400 cycles per second is spending 80% of its time doing GC and not doing the actual program, right? So I think if we want to bring costs into the space, we also need to consider that CPU also have 100%. Costs, right?
And I just point out that I think Jonas overlooked the great work done by Zessi and Kai back in with their elbow work, which looks at exactly this thing, how to measure the CPU cost of a GC. And it would have been good if Jonas's blog post mentioned that when he wrote that blog post, because that covered this in great detail, how we measure the cost of the CPU. So of course,
right.
I think everyone in this room knows that GC is a time-space trade-off, and we need to measure both, absolutely. But I'm nearly done. But there was a lot in that talk, and I just wanted to respond to it. So I just wanted to point out that we need to ground ourselves in what our costs are, both with respect to CPU and with memory. And if we don't understand the minimum heap size, and we go ahead and use 32x or 16x, the minimum heap size, then we've got an overhead there. And at the moment, most of the industry is facing a huge DRAM crunch. DRAM is not free. It may be marketed by cloud services as apparently being free, but in most cases, it's actually, we don't get the whole machine to ourselves.
I agree with that, and that's why I'm proposing that we sweep down from a representative heap size rather than sweeping up from a minimum heap size.
Representative size with respect to your deployment space, and I think if you want to write a paper, any one of us wants to write a paper because we're concerned, say for example, when you use paper, with a particular cloud service with a particular available memory, that's absolutely the correct thing to do. Yeah. But we shouldn't do that without forgetting about how much we're paying in memory. That was it. Look, and I will stop at this point because everyone else needs a chance to ask questions. But I want to say thanks again for raising this. But I would say that the prescription of ignoring the bottom line of how much memory the thing would take compared to how much you're using is extremely dangerous, particularly in an environment where DRAM is as expensive as it is today. And also finally the point that this is one part of the GC space, and there's a huge amount of other places where memory efficiency is the absolute premium, like on the phone and so forth.
Thanks for the question.
Hi. You have said very little about pause time and latency. Do you not consider it as important as throughput?
Quite the opposite, but that would be another hour. So I mean, we had some latency scores in the spec results that you have seen, right? I briefly showed the Cassandra latency result as well, but that's an entirely different bag of tricks, and I wanted just to have, let's say, a crisper story for this one. I'm happy to talk offline.
Hey. Thanks. So great talk. I'm Wenyu, and I'm the ARC author here. So can you go to like slide 40?
40? Yeah. Yep. Let's hope so.
Well, so I'm just having a minor question about like how you presented those.
Is this slide the slide that you want?
Oh yeah.
Yeah, excellent.
Well, I'm not going to ask anything about the XR. So the I'm just wondering how representative are the 4 heap factors here, and
sorry, can you speak?
Well, I'm just wondering how representative are the 4 heap factors here, and what's actually mean by calculating the mean over the 4 data points. To me, for example, if you remove 1.3x and adding 20x,
yeah,
the conclusion can totally change.
Oh yeah,
for example,
totally.
Can be consistently worse than G1.
Yeah. I do believe we picked up this technique from your paper, actually. So I agree.
Well, I'm picking the 3 heap factors for scalability analysis. I'm not intending to calculate.
Yeah, totally. I mean, I guess I should have a snake oil on this picture as well, because of course, just like I can control my results by choosing between default and large, I can also control my results with what heap factors I'm choosing, right? And I think that's really what this is all about, in a sense.
Yeah, okay. Makes sense. Thank you.
Okay, let's thank to the speaker again.
Thank you.